Hi there, everyone. Thank you very much for joining us today for our webinar on RF fundamentals. Before we get started, I'd just like to let everyone know that this webinar will be recorded and you'll be receiving an email with the recording, so you can go ahead and share it with anyone you think would be interested or rewatch it if you'd like. As you know, this is a three-part series on RF fundamentals. This is part 1. For your information, you've been automatically registered for all 3 sessions, and you'll be receiving reminders and login information for the next webinars a few weeks in advance. If you're interested in any of the other webinars we'll be hosting or to download any of the free resources we have available, such as white papers or application notes, please go ahead and visit testforce.com/academy and you'll find everything you need right there. If during the webinar you have any questions, make sure that you ask them in the Q&A section in the right side of the menu bar, and Rich Markley from Roden Schwartz will be sure to get to all of those questions as we get to the end of the presentation. And now, without further ado, I will hand it over to Neil.
So welcome, everybody. My name is Neil Jarvis. I'm an applications engineer with Roden Schwartz. I've been with the company 7 years now, I think, and previously, I worked at a competitor who will remain nameless because they can't remember their name. And I've been working in RF and microwave for 25 years. I've done design, test. I've been involved in some startups. I have some patents. So I've done a little bit of stuff in this world. So anyways, so we're going to talk about RF fundamentals. So kind of just a little housekeeping. Okay, so starting out, we're going to do intro to RF. So we'll talk about the electromagnetic spectrum. You know, what is it? Why do you care? Basic units of measure that we talk about in RF. Voltage, current, resistance. Hopefully you're all familiar with that. Power, sine waves, and Fourier representations. Free space propagation. Then we'll get into RF transmission characteristics just before lunch. Talk about transmission, some measurements, and some typical components. Okay, in the afternoon, basic signal model, noise figure, phase noise are the kind of noises that we typically measure. Intentional modulation, so that's disturbing the sine waves in some manner to put information on them. And so it'll be analog AM, PM, FM. Then we'll go into later more intentional modulation, but that's going to get more into vector or digital modulation. So that's kind of more of interest today. You don't really see a lot of analog modulation anymore. It's sort of Stone Age now, like me. Anyways, so digital modulation, we'll talk about constellations, what are they, and some other aspects of it. And I'm not going to get into like some of the really more complex modulation. So OFDM is kind of one of the more current things in fashion for wireless and technology. I'll kind of mention what it is, but I'm not going to go into a lot of detail on what it is. Okay, and then vector signal analysis is really how we analyze some of these waveforms. So obviously, you know, the point of this presentation is really to give you kind of a broad overview of RF wireless technology, but as you might expect, we have a few shameless plugs for our products. So anyways, so, you know, one thing to really focus on in this in general is wave propagation. So, you know, not everything is free space propagation, but really the thing that makes RF and microwave unique is the wave propagation. It has to do with the dimensions of the wavelength of the signals relative to the dimensions of the devices or things that they propagate through. So that's kind of just something to think about. If you drop a pebble into water, that's kind of what a wave propagation looks like. That's obviously a mechanical wave, so you're actually moving atoms within the water, as opposed to an electromagnetic wave where there's not actually a physical medium. It's energy. Okay, so again, this is kind of what we're going to talk about. So electromagnetic spectrum. So I don't know if some of you have seen this before, but you know, what we talk about typically, megahertz, gigahertz, kilohertz, hertz, that's the frequency or how fast that sine wave moves. So you can see here it starts out fairly slow, so this is really low frequency. And, you know, very low frequency things are are things like a transmission from a submarine, for example. They transmit at very low frequency signals to propagate through the water. And then you go to higher frequencies and you'll see things where, there's FM radio, AM radio, kilohertz, megahertz. We get into cellular, hundreds of megahertz. There's, tens of megahertz, broadcast TV, VHF, UHF. And then there's a lot of satellite stuff. Satellite's a big area in RF and microwave, and we have lots of customers, particularly locally, who do satellite stuff. And you see here, that's kind of broken out. Where is it? Basically, this is talking about kind of the size relative to the wavelength. So the wavelength, is how wide that sine wave is. So we're talking about the wavelength relative to some physical thing. So that's kind of trying to give you some sense of what this is. Okay, so we're obviously mostly probably engineers or engineering technicians. So, rather than the physics of it, you want to talk about what are you going to do with it, right? So some of the lower frequencies, we're going to talk about maritime navigation. So that's, shipboard type navigation, ship to shore. Then AM radio, so, maritime radio actually uses AM radio. Then we go up in frequency. You'll see more familiar things, VHF TV, UHF TV. I mentioned these before, satellite, microwave telecommunications, and this is where this breaks down. Satellite guys, they like to have letters to represent their bands. So that band is some frequency range. I'm not going to go into what they all specifically are. If you're interested, ask me later, and I can tell you. But satellite telecommunications, then you get up to really crazy high frequencies. You're going to talk about radio astronomy, things like that. And then, beyond that, it'll kind of get more to optics, which we're not going to cover in this. Okay, and this is kind of a funny one, is politicians like the spectrum because they charge lots of money for it. So if you've seen, a lot of the spectrum auctions they've had over the last 20, 30 years, they're selling spectrum licenses to Sprint, Verizon, AT&T for tens, billions of dollars. So lots of money. So excellent. Okay, so if you look at kind of the broad view of all the frequencies that are available and what things are in there, you can go on fcc.gov, and this is sort of a chart of everything that's encompassed on the electromagnetic spectrum. And it'll tell you, there's a band in here for satellites, there's a band for cellular, there's a band for point-to-point links for telephony. So this really says who's allowed to do what. And you might remember there's unlicensed bands. So if you talk about like 802.11 type signals or Wi-Fi type signals, those operate in specific bands which the FCC or whatever governing body, so FCC is in the United States, but other countries, Europe has ETSI, so that's their equivalent to the FCC, and they govern what you're allowed to do. So these unlicensed bands basically will let you make whatever you want as long as you adhere to certain rules. So you can only transmit at a certain power level maybe, or certain types of modulations, as long as you remain within that band. So again, that's where you'll see things like Bluetooth and whatnot. So you can see there's lots of stuff going on there. Okay, cellular's in there. Okay, so units, and I'm going to do this pretty briefly because hopefully you guys are familiar with this. But, the whole thing you find with RF and microwave is they talk a lot in dBs, right? So my first job out of college and the Navy was an RF company, and everybody was talking in dBs, and it was a little bit hard to process, being that, if that wasn't what you were used to. But it really makes sense once you get used to it, because, basically instead of multiplying these crazy huge numbers, right, you're just adding dBs. So it's like way easier. So you'll see that in a second. But these are kind of some of the common things you'll see. You know, you probably heard femtosecond, picosecond, nanosecond, microsecond, kiloohm, megaohm, gigabyte, you know. So those all should be somewhat familiar to you, and that's what they represent. Okay, and you'll see wide ranges. So again, dBs is, if you're talking about something, femtometer versus a yodometer, I don't even know what that is, but it's a huge range between orders of magnitude, right? So that 10 to the minus 15th to 10 to the 24th, if you were doing math to try and manipulate signals, you'd be multiplying things with like lots of zeros, right? Which obviously overcomplicates things. So instead, we're going to use the logarithmic scale. And this is really important for RF and microwave. Hopefully you're somewhat familiar with it. But it was invented by Bell Telephone, I don't know, maybe in the 30s or so. And they define a bell as a factor of 10. So really, the key thing with dBs is just remember the main thing is factors of 10. And there's a couple other important ones, but I'll mention. But anyways, so if you look here this is a spectrum analyzer display. We make spectrum analyzers, imagine that. So you'll see up here, this is in a dB scale, right? So this y-axis logarithmic scale shows 100 dB, right? So 100 dB of range is 10 billion. So that's 1 followed by 10 zeros, okay? So that obviously shows you a lot of range, and particularly when you're talking about things like free space path loss, where you have very large attenuations of signals or reductions in signal levels, you need to be able to see the whole range. So if you looked at that in a linear fashion, you know, this piece here is just sort of like that very top little piece. So that's kind of why we use log scales. Okay, and this is just, again, showing you some ranges for sound. I'm not going to get into that too much, but it's good for reference. Okay, so these are kind of the key ones to remember. 0 dB is a factor of 1, 2 dB is a factor of 3, 4 dB is a factor of 6. And then it goes the other way, too. If you want half, it's minus 3B. If you want a fourth, it's minus 6 dB. So these are kind of the two, other than 10, that you want to remember. And then everything else is really just factors of 10, right? So you see here, 10x power is 10 dB. 20 dB is a factor of 100. So it's 2 zeros, really, right? So that's what the 2 comes in. So if you wanted to know what's a factor of 250, you'd say, okay, well, if I know these and I know these, I'm going to say, what's 1,000? Well, 1,000 is 30, right? And then what's a factor of 4, or 1/4, is minus 6. So you take the 30 and subtract 6. So, you know, if you talk to an old-time microwave engineer, like, they almost never have a calculator out. They're just adding and subtracting stuff in their head. So, you know, my first job, guys, I had my calculator out all the time in my spreadsheet, and they're like, you know, put that away. You should be able to do this all in your head. So, you know this page. Okay, so hopefully this, again, is stuff you're familiar with. Voltage, current, resistant, Ohm's law. You know, this is kind of the basic, most basic thing in electrical engineering, right? V is IR, Ohm's law. Okay, and you can move that around, solve for current, resistance, whatever you want. Okay, so resistance versus reactance. So resistance obviously is just a fixed current level, right? Or fixed voltage level. It's not varying with time. Okay? So, you know, in more real-world circuits, you're going to see, particularly with higher frequency stuff now, there's capacitance, right? So, you know, in my earlier day, you would see obviously lots of RLC circuits with big wired leaded capacitors. You don't really see that all that much anymore. They're normally chips and things, but one of the things in RF you find, particularly things like signal integrity, you really have to take into account the capacitance, the inductance of the actual traces and things on the board. So when you get to really high frequency signals, you care about, puffs and point puffs and, things like that. So the key thing here is capacitors resist changes in voltage, right? So you can't, if you think about like a clock, we do lots of stuff with clocks, where you obviously want a square wave going up and down very quickly. Well, if you have some capacitance on the PCB or on the device or whatever it is, you're going to find that you can't switch it on and off fast enough, right? So that's a common thing in signal integrity is like, wow, I can't get the edge rate high enough. I can't get that to switch fast enough. So what's my problem? Well, it might be that I have too much capacitance, okay? Then, similar thing for inductance. Inductors resist instantaneous changes in current. Okay, so similar thing if you're trying to drive a lot of current, same thing might apply with a clock or something like that, or even a data line. You need to be able to change the current very quickly, and if you have a lot of inductance in your line, you're not going to be able to do that. Okay, so sinusoidal signals and reactance, and again, hopefully most of you are somewhat familiar with this. Just like V equals IR, we can find a mathematical representation for the reactance. So that's similar to resistance, but as a function of frequency. So you see here, voltage and current are in phase with a square wave for the resistor, but when you put that capacitor in here, the capacitance causes the voltage to lag the current, right? Because remember, the capacitance resists changes in voltage. Okay, and then similarly for an inductor. Inductance causes the current to lag the voltage. Okay. Okay, any questions so far? Hopefully this is all this is the less interesting stuff of everything. Anyways, so talk about sinusoidal signals. Okay, so now we're going to get into a little trig. Okay, so the key things that we care about, and this really started back more from analog modulation, analog signals, is frequency, amplitude, and phase. So when we create modulated signals, or signals that we want to put information on, we're going to modify one of these, and you'll see that in a sec. Okay, so hopefully you remember, too, that I can represent a sine wave as a phasor, right? So it has a magnitude and a phase angle, as opposed to just looking at the sines and cosines. So this gets more important as we get into digital modulation and digital signals. So if you look at Euler's formula, where this kind of comes from, you're saying that e to the ix is cosine plus sine. Okay, so this is really what we care about, is our signals are sines and cosines, and we want some other way of representing them. So that's where, if you've done basic engineering or technician, basic electronics, you'll see that I as opposed to, or J. Okay, so what is that? That I is the square root of -1, but engineers don't use I, they use J because I is already used for something else. Okay, but we can get these cosines and sines by using complex math with Euler's formula to get these same vector representations. So, sines and cosines are things that we're going to be using. We're going to manipulate these sines and cosines to put information on them. And you'll see that shortly. Okay, so if you look at a sine wave, so really, the real world is analog, right? We probably all know that. When you talk or listen to sound or things disturbed in the water or whatever, They're analog waveforms. We don't like to process analog waveforms. There's more stuff we can do with it in the digital realm and save it, store it, transmit it, put error correction on it and things. So we like digital, so we're going to want to convert that to a digital signal. So that's kind of what the point of all this is. But if you take that sine wave and look at it, the basic sort of characteristics of a sine wave are a sine omega t plus alpha. I usually put phi there. But anyways, so A is the amplitude. That's how big it gets, right, peak to peak. Omega is how fast it's varying, right? So if you remember that diagram where we went from really low frequency to, X-rays, that's how fast this thing is moving. And then phi is really kind of moving this thing left and right. So we can put sort of like an offset on it. And all of those characteristics of that sine wave we can use to put information on it. Okay? So another way of looking at that is to look at it with respect to a phasor, right? And we like phasors, and when we get into like IQ modulation, this is going to become really important. But you can see here, if I look at this phasor, it's basically showing me some point on the sine wave, right? So there's an amplitude associated with it and a phase. Okay? Same thing applies to a cosine. And really a cosine is a sine wave with a different phase offset, all said and done, right? Okay, so A is the magnitude, that's peak to peak. I got ahead of myself here. Angular velocity or frequency. Okay, 2 pi over omega is the period. Omega over 2 pi is the frequency in hertz. And the phase angle is the lead or lag, so it's basically, again, this moving back and forth. Okay, so phase angles and the complex plane. So basically, what we're going to do is we're going to use these different sine waves, and we're going to put information on them in that complex vector. Okay? So this is a thing just to play with. I'm not going to pull it up right now. Well, I guess I could. But it's just a nice thing with some of this that it's good to just play with these things a little bit. Not letting me do it. Okay. All right. Well, I'll skip that. Okay. So power. So any questions, comments? No? Okay. I'm going to start calling on people soon, but you might win a prize. Anybody know what movie that was from? Nice. That's when I know I'm old, if you don't know what that movie is, because I get that kind of stuff a lot. Okay. So power requires both current and voltage. So if you look at, you take a balloon and you get that static electricity where it plays with your hair and whatnot, and you can zap your kids. I do that all the time. There's no current, right? Really high voltage, no current. And then you can have high current and no voltage, too, right? Lightning bolt, both. Okay, so power and its units. So typically we're talking watts, so volts times amps. And obviously if you go back and remember Ohm's law, even when you're doing like fancy DSP and whatnot, you're still going to refer back to Ohm's law. It's the basic premise of a lot of electrical engineering. So you can take this and then substitute one of these in here if you don't know. Maybe you know resistance and current, but you don't know the voltage. So you can substitute. Okay? So that's a common thing people would do. That's where you see the I squared R, B squared over R. Okay. So commonly, you'll see ratios of things, right? So an amplifier, for example, it's making a signal bigger, right? So you want to know what's the output relative to the input. Okay, so, in a simple case, you'd say it's a factor of 10, right? So that ratio would be the output is 10 higher than the input, so you'd say 10 over 1. But again, we like to talk in logs in the RF and microwave world, so instead of saying times 10 or times 100 or times 1,000, you'd say 10 would be 10 dB, a factor of 100 would be 20 dB, a factor of 1,000 would be 30 dB. Okay? And then remember, 3 is always double. So this one you see a lot. It's actually funny, I had one of my jobs, I couldn't get the gain of this amplifier quite as high as I needed it to, and so I went and asked my boss, and I said, I'm off by 3 dB, is that good enough? And he said, well, how'd you like a 3 dB cut and pay? So then I went back and started messing with stuff. Obviously, I didn't want that. So dBs, again, this is really to talk about big differences in signals. So, when we talk about propagation in a little bit, you're going to see that when we have propagate over a distance, things sort of grow in a spherical manner, right? So if I send a signal out from a point to go somewhere else, if you think about it like the signal is going to start at an antenna and it's going to grow like a sphere, right? So as you might imagine, if that same energy is perfectly distributed among that sphere, it's going to get smaller really quickly over distance, right? So because of that, say you go a mile away when you transmit a signal, it's going to be a lot of dBs lower. So rather than, again, a factor of maybe 10 million or something, you'll do some number of dBs. So we have some good app notes on this, so look on our website. Anyways. Okay. So, I thought we just did this. Okay, so this is really talking more about ratios, right? So we talked about, well, it's not talking about, this is talking more like absolute numbers, right? So if you think about the dBs, so when I said a gain is of 10, factor of 10 is 10 dB, or gain of factor of 100 is 20 dB, well, what is my reference point, right? If I said I have a watt, and now I want to make that watt go up by 10 dB, a watt is a linear number. It's not a logarithmic number, right? So because it's a linear number, you've got to figure out a way to get it to be a logarithmic number. So what they've done is they came up with what we call a dBm. There's dBWs and other things too, but the most common one you'll see around here doing cell phones and wireless LAN and that kind of stuff is a dBm. So it's really a dB relative to 1 milliwatt. Okay? So if you do that ratio where you're putting in that milliwatt, it turns out 1 milliwatt. Sorry, I can't speak. So 1 milliwatt is 0 dBm. So this is kind of one of those good ones to remember. And again, when we're talking dBs, really if you remember that, that's all you got to remember, right? Because if I say, how much is 2 milliwatts? Anybody? 3, right. 3 dBm. So I'm going to give out prizes now. So you win a wireless travel router. Yeah. I got more stuff too, so maybe you guys will perk up a little. Anyway, so 10 milliwatts, factor of 10, so 10 dBm. 1 watt, so how many milliwatts is a watt? Anybody? This is an easy one. Okay, I'm going to give you that one. Okay, you get a book. I'm going to keep doing this till my bag's empty. Maybe not all right now. But anyway, so 2 watts. I'll just leave that one. 33, so obviously adding that 3 to get a factor of 2. So, when you get into some of these other ones where some number in between these, usually you just kind of estimate, right? You can go in and do this, but, you say 11 milliwatts. Well, I know what 10 milliwatts is. And I know what 20 milliwatts is, and it's somewhere in between. Okay. Okay, so common power levels. Again, this is just kind of a nice reference thing. So thermal noise. So this is kind of an important one in RF in general. So really what that is, if you went out into space, hopefully you're not going to do that because then you'd die, but out in space, thermal noise, so that's basically saying I have no environmental noise. You know, if you take a spectrum analyzer and you hold up an antenna, you'll see a noise floor, right? It's basically the noise of the environment. So there's spurs and things from things transmitted, but there's, you know, stuff from the sun, just the energy in the environment. So this one's an important one to know because really when you try to determine the performance of your system, particularly like propagating through space, you always want to know, like, how much bigger is my signal than that? Okay? And we'll get into some calculations with that. But, you know, that's an important one to know. So this is input receive level for a GPS satellite, and that's a pretty small number, right? You think that relative to that. That's crazy. Femtowatts. Minimum receive signal of a wireless network. So that's all these 802.11, A, B, G, N, alphabet soup, whatever, minus 100 dBm, right? Small number. That's 0.1 picowatt or 100 femtowatts. No, pico, yeah, whatever. Maximum receive power, minus 10. Bluetooth, LAN in a laptop. UMTS, mobile, GSM phone. These are getting a little dated, I think. Citizen radio. Again, that's a little dated. Anybody have a CB radio? I'm sure they don't. Okay. Yeah, it's funny. When I started in RF, a lot of people had CB radios, particularly the guys I worked with, and they said, like, they didn't used to regulate the power very well. So there were guys who'd have a radio, and he'd be driving along, and then he'd key his mic, and his car would stall because it sucked so much power out of his thing. So, you know, people like power. Ugh. Anyways, I digress. So, what other interesting things? Ham radio, geostationary satellite, microwave oven. You know, that's a lot of juice right there. So, you know, that's why you don't want to stand right in front of your microwave while it's running. You find, too, like, I did some stuff at Cisco years ago, and they put an access point right above the microwave, and then they found that throughout the day, particularly at lunchtime, it didn't work. Imagine that. So, anyways. Okay, so Fourier. Hopefully you've all heard of this, but really, Fourier is it's the basis of a lot of DSP and stuff you really see in the Valley now, signal processing and things like that. But it's really ways of creating signals using frequency and time domain approaches. Okay, so if you look in the time domain, so this is, you know, like me singing a perfect note, ah. So that's a sine wave, has some given frequency and amplitude like we talked about. If you looked at that in the frequency domain, so this is going to my spectrum analyzer, you'll see one tone, right? So you never see one perfect, infinitely narrow tone. That doesn't happen. That's a whole other conversation. But if you did have a perfect sine wave, you would get one spike at that one particular frequency. Okay? And then if I took 3 times that frequency, obviously I get a tone somewhere else, right? Then I can do 5 times that frequency. And you're wondering, why am I doing these particular integer multiples? Well, it turns out if I take odd harmonics of multiples, I can actually make a square wave, right? So you can look in here where things add and subtract, but all said and done, to generate this square wave, and obviously, particularly in the Valley, you know, you're going to want square waves, right? There's square waves in all data transmissions. So that that would be more like a clock signal. So a clock signal, as opposed to a data signal, is perfectly periodic, right? It means there's just as many ones as zeros. So it just goes up, down, up, down, up, down, up, down, up, down, infinitely number of times, square wave, perfect edges, blah, blah, blah. So I take that first one, then I'm going to add the third harmonic, then I'm going to add the fifth harmonic, seventh harmonic, and it turns out when you do all that, that's how you make a square wave, right? I'm going to take all these odd harmonics, and the better square wave you want is going to require more and more of these. Typically, you won't see that many, particularly as you go up in high frequencies. So if you think about, like, if I wanted a 20 gigahertz square wave, right, that would mean this would be 20 gig, then that would be 60 gig, 3 times 20, 5 times 20. So you're going to get up to like crazy high frequencies really fast. And if you look at, the challenges in making transmission lines and things, which I'll talk about later, once you get above, tens of gigahertz, things get a lot harder. So effects of errors in representations. So this is basically just saying when you put other tones in here, and this is what typically happens, is you want that, where this is kind of exponentially decaying, more or less, 1, 3, 5, 7, 9. But when you actually look on a PCB that's maybe has vias and transmission lines on it, or cables or connectors, or pins from devices, these things get distorted. So, this is what keeps me fed, right? It's like people make a board that they want to work at 50 gigahertz, and they build it, and it doesn't look like that. It looks like that. So why does it look like that? And then you have to go and look at every interconnect on the board and say, okay, I put it in the connector and I look here. Does it look like that? No, it looks like something else. So then you break down and figure out, okay, there's a connection here or a via here or something, and then you characterize what that is relative to what you modeled, and then try to isolate it. So that's kind of the big challenge. So that's really one of the interesting things for me in my lifetime is, it used to be that RF and microwave, this stuff, was a distinctly different thing from digital stuff, right? So when stuff was like kilohertz, megahertz versus gigahertz, this stuff was completely irrelevant to a digital engineer, right? But now, because the frequencies have gotten so high in the digital realm, the digital guys have to know this too, because if you're trying to send a digital signal, a clock or whatever, data signal, through a transmission line, the physics causes you to need to look at it in this regard, in terms of more of a microwave type signal. So don't think you can be a digital guy and escape all this. Okay, so Maxwell's equations. I'm not going to go into this in a lot of detail. If you've done EE, hopefully you've done this. I think everybody still does E&M. I know they've been watering that stuff down, you don't have to do comms engineering and stuff anymore, but the first interview I ever had after college, the first question the guy ever asked me was, tell me Maxwell's equations. Yeah, and I do you want it in integral or differential form? And he said integral. I'm like, I got nothing. But he liked my answer, so I got hired, actually. So anyways, so Gauss's law, electrical flux, it's basically, if you enclose a surface, the charge isn't really going to escape it. So things where you look at a chamber, they really take advantage of that. Is if I make a perfectly enclosed chamber, no signals are going to get out or get in. Okay, there's a similar for magnetism. We're not going to really talk magnetism. Faraday's law, work per unit charge required to move a charge around a closed loop equals the rate of decrease of flux, blah, blah, blah. Ampere's law, Like I said, I don't want to go into that. I don't want to relive that first interview I had. So, laws of Faraday and Ampere's law. A changing magnetic field creates a perpendicular electric field. Okay. Changing electric field creates a perpendicular magnetic field. And an electric current will also create a magnetic field. So in the end, why do I care about this stuff? At some point, now we're going back to RF and microwave as opposed to, digital stuff. Maybe I want to propagate this signals in the air, right, as opposed to down a transmission line or cable or on a trace on a PCB. So how do I do that, right? So I'm going to use an antenna, okay? So an electric current in a wire creates a magnetic field in space around it. So really what you're going to do when you design an antenna, if you select the correct geometry relative to the wavelength of the signal, you can have, because of the electric and magnetic fields feeding off each other, you can actually create a signal that's going to propagate through free space, and that's more or less what we're going to do. So it's going to convert conducted RF energy into an electromagnetic wave, or an electromagnetic wave into an RF conducted signal. So that's more on the receiver. So, antennas are symmetrical, so they're going to transmit and receive, basically does the same thing. Although, at some point, usually you're going to put an amplifier pretty close to the end of that antenna. On the receiver, there's a low noise amplifier. On the transmitter, there's a high power amplifier. Okay, and that's what it looks like. So kind of going back to the pond thing, right? So that E and H field is time varying. Okay, so basic antennas. And I'm not an antenna guy, so bear with me. So conducted waves coming from your receiver or transmitter, or coming from your transmitter or going to your receiver, right, is coming to the antenna, and that antenna is going to convert that into electromagnetic wave that will radiate out in space. Okay, and designing antennas, pretty much, there's not any, I'm assuming there's no antenna designers in here, right? No? Good. They're all weird people. That's been my experience. Good people, but anyways, I had a few bosses that were antenna engineers. So if you are one, or you can come and give me a hard time later. Okay. Okay, so propagation. So this is kind of more a little bit what's interesting. So, when I design a system, typically, if I was a system engineer and I was going to do make a link, right? So I basically, if I have my cell phone here and I have my base station way down there, I want to transmit a signal from the base station that I'm going to get here. So, I obviously have to propagate that signal. So typically, you're not going to go design an antenna. You're going to go to a site or whatever and then buy one. But you need to know what characteristics you care about. So free space path loss. So I mentioned this earlier in brief, but a signal transmitted by an isotropic, that's a nice word, which means uniform in all directions. So just think about it like a sphere, right? So if I stimulate an antenna, it's going to grow like a sphere out in free space. And that's a particular type of antenna. We do things to change that shape, but in simplest case, I'm going to propagate out in a sphere. Okay, and the area of that sphere is just governed by the basic geometry, 4 pi d squared. Okay, as the sphere expands, the intensity of the signal over the surface area decreases per the inverse square law. So it's basically just telling you that as this gets bigger, the amount of signal in a given area gets smaller because it's distributed over a bigger sphere, right? So if you start here and the sphere is that big, obviously there's more intensity in one given region, and if you take the same size region on a bigger sphere, that is distributed over a bigger sphere. So that's really kind of the key thing to remember. And, it's really simple geometry for all intents and purposes. So attenuation, that's more or less signal getting smaller, loss. It's a fancy way of saying loss. Okay? All objects will absorb or attenuate RF. So, when you, if you have your cell phone, and you walk behind a brick wall, obviously sometimes your phone call drops, right? And it's because it's getting attenuated by that signal. There's other things that happen too, but that's kind of one of the primary ones we're going to talk about. It's simple. So different materials have different attenuation characteristics. And I've actually done stuff in a startup I worked at where we were actually making tools where you'd set up a network in, say, a campus, and you would tell it what the room looks like. So you'd say, okay, I get a drawing from the architect, and what are these materials? And then it'll tell you where to put the access points, right, so that I can get equal coverage throughout the building. But the thing that was kind of funny to me is not knowing anything about construction is you get those drawings from the architect, and this is like a building that's permitted and all that, and it's completely wrong, right? They'll say there's like a wall here, and there's no wall. There's like a closet over there, and it's completely wrong. So that was pretty surprising to me, but anyways. So, when you set up a network, so again, more look at the system engineering aspect of this, you want to know, like, that wall over there, if I put a transmitter here to transmit to a cell phone on the other side of that wall, how big is that signal going to be on the other side of that wall? Because there's a minimum signal level your cell phone will be able to receive and transmit back at. Then there's reflections. So reflections are just like what it sounds like. It's signals bouncing off. But the thing that's a little more interesting, you think about like a mirror. That's my reflection, right? I won't look at that too much. But anyways, so you have reflections. So there's just the reflection of the signal. But what happens is signals bounce off things, right? So you have the attenuation, but then we have a signal will bounce off a metal object and reflect back. And is that me? No. So signal reflects back. And you think, on the one hand, that could be useful, right? I could use that signal, and maybe I can receive that signal, process that signal. But the thing that sometimes happens is that signal will add or subtract with the other signal that's going the other way. So it'll screw up your signal. And that's why when you're driving down the road and you're on the freeway or whatever, and maybe the call drops out and whatever, it's usually because of reflection. So it's things adding destructively, constructively to that sine wave to change the signal amplitudes. So actually designing a network that'll work when you drive a car is really hard because the characteristics of the signal as you move over higher velocity, they change more rapidly, right? So they put lots of stuff in the signal, error correction, and things so that there's the information may be repeated over time to try and take care of that, but it's a challenging thing. Okay, diffraction and refraction. Things get bent. So, this is kind of more of a third order effect, so I'm not going to go into that in a lot of detail, but there's other effects that can happen that again make this problem more difficult to deal with. So multipath, I kind of mentioned this. This is really, I got ahead of myself there, but this is the signals reflecting constructively and destructively, right? So there's the base station up there, and there's antenna on this van. It says Rohde and Schwartz on it, of course. So this guy's sending a signal, and normally when I'm setting up a link, you'd say like, I want to talk from there directly to there, right? The yellow line. So I set up my link. What's the distance? What's the free space path loss? 4 pi d squared, blah, blah, blah. And I know what the signal level is. But the reality is that's not the only signal that gets there, right? So that signal, there's also one that bounces once off this building, bounces twice, whatever. And this is more of a statistical thing. There's no way you could measure every possible reflection that gets there, every possible multipath. But your receiver needs to be able to know what's coming. Because aside from the adding constructively and destructively, what can happen is I'm talking to you, and I said hello. The hello gets there, right, on this signal. But then the hello gets there a little bit later here. So then you'll hear like an echo, right? If you didn't know to deal with that in the system, you'd hear hello, hello. Then you'd get the third one, and you hear hello, 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 and so on until you got all the multipaths. Obviously, that's not a desired effect. You don't want to listen to me any more than you have to. Okay, so that's kind of it for the first section. So any questions, comments? Yeah, please. Hold on, let me grab the microphone. Where did I put it? There it is. There you go.
On the slide where you showed the different power levels, I was curious,
Yeah.
Why is a GPS receiver signal so low compared to all other radios and still we are able to detect, at minus 127 dBm? Like a wireless LAN or a 3G, 4G won't work at that frequency.
Yeah, I mean, it gets into a lot of more really complex things in the coding of the signal, but it was really specifically designed to do that. So like if you look at what GPS was originally designed to do, it was designed really for military, right? So they wanted it to be able to work in harsh environments, low signal levels, be able to work with interference and things like that. So it really was specifically designed to do that. Without getting into, it's more of a coding thing. So there's like I don't know if there's any signal processing gurus here, but there's things that like you can do in the rake receiver and whatnot where it'll actually let you have processing gain beyond that physics of what I talked about. It's a great question, but it's a little bit beyond the scope of what we're going to talk here. Yeah.
Just as a follow-up, won't we always want like signals to go that low? For example, for Wi-Fi, people have big homes, and and people always complain my Wi-Fi doesn't work. Is this also a design factor we can do in Wi-Fi, like people did in GPS, or it comes as a trade-off that we are not willing to do for Wi-Fi that we did for GPS? I'm sure there's a logical
it's a good question.
reason.
So in terms of Wi-Fi, the first answer to that is like when you set up your Wi-Fi network, it'd be really good if you knew what you're doing, which most people don't. It sounds a little tongue-in-cheek, but the reality is, people will put their Wi-Fi thing over their microwave or whatever. So that's part of it. In terms of what the functionality of a Wi-Fi network and how much power it's allowed to transmit and things like that, a lot of that's really more governed by the beginning stuff, the FCC and whatnot, because the stuff that the governing bodies really hate is unlicensed stuff, right? So if you have a licensed spectrum, so like Sprint, for example, we make products to help find interference, right? So I've gone out with guys with Sprint, and we go out with direction-finding antennas and whatnot and say, oh, look, there's an interferer here, and you go over, knock on the guy's door and say, dude, you're transmitting stuff on Sprint's licensed band that they paid $5 billion for. You better turn it off right now, or it's going to cost you $100,000 a day, right? So on a licensed spectrum, that's one thing. On an unlicensed, it's basically you're doing whatever you want. And because you're generating a signal, in that unlicensed band, one of the problems that often happens when things get broken is it might spill over into another band, right? And you saw how busy that whole map of things are. So, people who do that for a living are really nervous about the unlicensed stuff, the 802.11s and whatnot, because they basically can interfere with other things that may be like really important signals, like guys who do, safety, like police, fire, whatever, that kind of thing. Yeah. Thanks.
I think kind of what he was going at is what's limiting our receiver sensitivity such that we don't need as much power in the ISM band in order for Wi-Fi to work. So why does a GPS receiver work at negative 127 dB, whereas Wi-Fi needs a higher signal strength in order to work?
Yeah. So, I mean, without getting into the architecture of what's in there, but realize for a Wi-Fi receiver, it's a two-way link, right? And you want to send data in both directions at a fairly high rate. And GPS is a one-way link, right? You're typically not transmitting GPS data. So it's much easier to make something that's not a symmetrical link, right? And even 802.11, like, it's never going as fast usually up as down, right? Just like on your cell phone, right? It's always going slower because when you're transmitting, you can kind of figure out what somebody's doing if you're the big, fancy, expensive thing versus the end client user. So I know that's not a very helpful answer maybe, but it really gets into the architecture of how it was designed
it's a trade-off between data rate and
right. Yeah, among other things, yeah.
I actually had a question. When you were showing the Fourier series representation and then what it would look like on a board, what would cause it to be higher? I can see attenuation occurring, but you were showing amplitude errors of higher than 1. And what could cause it?
So, oops, I think I'm going the wrong way. Sorry. Of course, it's going to go way back. So, like in here, you're saying here?
Yeah.
So
like your 9th
the 9
is 2 times what it should be.
So it's typically this would be a reflection, right? So if you think, and I'm going to get into this in a little bit, you'll see it more clearly. But if you think about, if I have a sine wave that goes this way, right, and then I get a reflection back because I have a mismatch there, and that signal is perfectly in phase with that signal, they'll add constructively and make a bigger signal.
Do you see a future for Wi-Fi type of signals and later revisions of the specifications? Do you see a future for that?
Oh, I mean, Wi-Fi is not going anywhere, for sure. And in fact, want me to go this way? Okay, I'll be with you in a sec. So Wi-Fi's not going anywhere. It's a great question. And in fact, if you look at some of the more cellular type standards, they actually have like LTE over Wi-Fi, right? So, the guys who make the cell phones want to be able to take advantage of that spectrum too. So it's not going anywhere. And in fact, a lot of the LTE signals are kind of, or Wi-Fi signals are kind of trying to look more like an LTE signal. We have guys here, they're hiding from me, but who are more LTE experts that can get into more detail on that. But it's a good question. But yeah, Wi-Fi's not going anywhere. But the tricky thing with the Wi-Fi signals, again, is they're intended to be really low-cost consumer products, right? So there's not the same degree of rigor done when they test them and characterize them and verify their functionality on the network. That's a really big thing for like a Sprint or a Verizon or an AT&T, where they want to make sure everything plays nice with each other. And then when you throw in some cheapy thing that you bought at Fry's for $18 versus your $1,000 iPhone, it's a problem. So, sure. Anybody else? Yep. Sorry.
So I can add some points to help you answer those
Okay,
GPS
great.
versus Wi-Fi.
I like
because
help.
the GPS has the coding game in their baseband. It's like some CDMA coding.
Yeah,
so
processing gain, right.
Actually, the signal level is even lower than the noise floor.
Yep.
That's why they use quite a long time to do the averaging of the signal to extract some statistical information from the satellite.
Yes.
But that's why if you use GPS only, you have to wait for quite a while to track the satellite.
Right, right.
But this is obviously not good for Wi-Fi.
Yeah.
You cannot wait. Yeah.
Yeah, you don't want a 1 hour wait for your call to connect.
Yeah. Once it's tracked to the
question.
satellite, but the data rate is still very low, just
Right.
to record several positions. So that's why the signal sensitivity can be very low for
Great.
GPS.
Thank you. That was very helpful. Thank you. Anybody else? There you go.
Yeah, when I was going to university, we had a hobby called DXing.
What's it called?
DXing,
Okay.
which is catching shortwave radio signals where you are resident using
Cool.
a dipole antenna.
Uh-huh.
So what we used to do is we were the eyes and we were the ears to the broadcasting company, and we had a rating called SINPO.
Okay.
Signal strength, interference, noise, propagation, overall performance.
Okay.
And you send the information to the broadcasting station, and they send you a QSL card, which is acknowledgement card.
Okay.
And sometimes
Cool.
you get a price note. So my question is,
Yeah.
taking all the information you provided, you talked about signal strength, you talked about propagation and noise interference. So is that still a measure? It's an analog thing when you're listening and providing the feedback. Is that still in practice, or?
Yeah, so that's actually an interesting question. You're going to get me off on a tangent, but
We talked about hand radios.
no, it's a great question. Okay, so in one of my previous lives, I was in the Navy, and I also worked in a defense company. So we did interferometry. So it's basically what our job was when you go into a combat zone, you want to find where anybody is who's talking on a radio, right? If you go back 40 years, it would be find the radar in the place, Baghdad or whatever, and blow it up, right? That was the old paradigm. So now it's find everybody doing anything anywhere, right? So there's a guy on a bicycle riding his phone and he's talking to somebody. Who's he talking to? Where's the signal coming from? Where's the signal going to? And what's the information that's being transmitted, whether it's data, voice, or whatever. So it's still a huge thing. Direction finding, I guess, in the broader context of it. So there's signals out there. We actually make tools for interference hunting. So it's really direction finding tools. So if you look from a military perspective, it's what I just mentioned. But commercial people use them too. We actually had an interference hunting thing where when the cell guys started with LTE, the noise floor for LTE was, 30, 40 dB lower than anything before, right? So when you had cell phones operating in that same band, before it would be, hey, it works great. Now there's stuff way down there that is interfering. And it was a lot of things. You'd find like electric motors were generating noise. You'd find neon signs, and even stuff for electrical, utility things that had dissimilar metal contacts might be generating a noise spike at minus 95 dBm. And their noise floor was minus 130 or something like that. So yeah, that's a big thing, and we make stuff for that too. It's actually really good.
The surprising thing was that we would get, say, from Radio Denmark, we would get a response back saying that's surprising because we were not broadcasting to Pune, India. It's meant to be the other way around, so there's multiple reflections.
Yeah, reflections and yeah, and you find too, that's a good point, is, I didn't really talk about like ham radio, for example, but the whole premise with ham radio is when I send a lower frequency signal, it's going to bounce off the environment depending on, time of day and, the ionosphere and whatever. But it'll bounce on between the atmosphere and the ground, and go somewhere else in the world, right? And you kind of don't know where to some extent. So that's kind of what ham radio does. That's great comment. Thank you.